Okay, we're going to start today on page 15 of your yellow packet. You'll notice on the top right corner of each page it has some incorrect information. It should just say Quiz Friday, not Quiz Tuesday 11/29. That's left over from a prior year. I'm sorry that was not taken out. So on page 15 is our warm-up. This is good practice for your Quiz Friday. We're going to pause the video here for you to sketch the graph of these derivatives. So sketch the derivative for each of these equations. Okay, so if I think of the function y equals 4, that's a horizontal line. So the slope, or the derivative for y equals 4, always has a slope of 0. So that is a horizontal line at 0. For negative x squared, this one you would need your calculator for, and you would have to do the end deriv, or you have to do the calculate from the graph menu, because the slope is not constant. And when you get your final graph, you would have the point 0, 0. You're going to have the point negative 1, 2. So these are some of the slope values you should have gotten for f prime of x, and then when you draw your graph, it's a linear graph connecting these points. Okay, so now for page 16, we're going to start finding the derivative function. To review, if we are given tables of values, or if we find tables of values, if they weren't given to us, we can calculate the slope at 1. So here's the values for 1. So I would find the slope. Let's do to the left of 1 with these. Remember, it's y minus y, so that's 1 minus 0.998. And the denominator is x minus x. And when you calculate that in your calculator, you should get around 2. Just to be safe, we should do the slope from the right-hand side, from the other side of 1. So that's 1.002 minus 1 divided by 1.001 minus 1, and we also get 2. So we can say that the derivative, the derivative at 1, so the slope at 1 is 2. Now, if you trust my slope calculations, we would get the slope at 2 to be 4, and we're going to get the slope at 3 to be 6. And I would calculate that by doing y2 minus y1, x2 minus x1 from the left and from the right, and see what they're approaching. Now, that seems like a really long way to do this. So we're going to come up with a more efficient way after we generalize the function here. So we go 2, 4, and then 6. So that appears to be that if I do 2 times 1, I get 2. If I do 2 times 2, I get 4. 2 times 3, I get 6. So if I do 2 times x, that would give me the slope at any point. So now if I said to you for this function, for x squared, what's the derivative at 10? You could plug in 10 for x and get 20. What's the slope at 5? You could plug in 5 for x and do 2 times 5 and get 10. So you wouldn't have to do these calculations every time. You wouldn't have to go through the limit every time. You wouldn't have to use end deriv or the calculate in your calculator for every single point. You could just substitute in values for x, which would be the most efficient way. So we can actually develop this 2x algebraically instead of looking for a pattern. I'm horrible at patterns. I'm not very good at seeing them. I don't like them. I would much rather go through an algebra process. So if you recall from our last unit, we found the derivative at any x value, but we actually used a number for a. Well, we can do the same thing and calculate the slope, but instead of having an a, we're just going to have an x. This is the general definition for the derivative. We can find the derivative equation when we have any x, just like when we had any number a. So f of x plus h, for back from the top of this page, f of x was x squared. So f of x plus h, I'm going to plug in x plus h. That means multiply it by itself. And now we're going to have x's and h's. So x times x times h times x, h times h. And then I can combine like terms with these xh's. That's 2xh. And now this trinomial will replace this part in my limit. And f of x was x squared. Just like before when we had numbers, these have to subtract to 0, and they do. So the pieces that we're remaining with can I simplify this fraction to eliminate h in my denominator? So I can factor out an h from both pieces of the numerator. Because I can do that, the h's divide away, and now I can substitute in 0, and we get 2x. So the derivative of any x is 2x, and that was the pattern that we saw above, calculating the slope with the numbers. So we're going to repeat that formula given this definition. So for example, your quiz on Friday is going to say, using this formula, prove that f prime of x is 4x plus 1. I'm going to give you the answer. What I want to see is, can you do the algebra through this limit to get to the actual derivative equation? So let's plug in everything and do all the algebra. This is the limit as h approaches 0. Now f of x plus h, I have to plug x plus h in for both x's. If you want to put parentheses around that to show that it's this x that's added at the end, you can. Then I have to multiply it together and combine all my like terms. Distribute the 2. Now there's no other like terms that I can combine because this is x times h, and these are x and h separately. So when I go up here to my limit, it's 2x squared plus 4xh plus 2h squared plus x plus h minus 2x squared plus x, which is my original function, all over h. Now here's the key part. You have to distribute this negative. If you don't, your algebra for the rest of the limit is not going to work. We have the limit as h approaches 0, 2x squared. So I'm recopying my numerator. Now minus 2x squared minus x. ideally what I need to happen, not ideally, but it has to happen for this limit to be able to be evaluated, is anything that doesn't have an h has to subtract to 0. And it does. 2x squared minus 2x squared is 0, and x minus x is 0. So now the three terms I have left all have an h in them. And because all three of these terms have an h, I can factor out an h. Here, this is going to be 2h, and this one's going to be 1. So the h's cancel. Now I can plug in 0 for any h. So that's 4x plus 0 plus 1. And we proved what I said up here the derivative was going to be. We did it. Okay, let's try that again for b. Prove that the derivative is 6x minus 2. So we'll pause the video here for you to do the work. Okay, so now I'm going to plug in x plus h everywhere for every x value. I have to multiply this together, which we've already done twice now. I have to distribute the negative 2. Now I have to distribute the 3. So these problems are even more algebra work than what we were doing last unit with just the numbers. Okay, so this is the first half of my numerator. In my way. Okay, so I'm just going, squeeze it in over here, so that's the limit as h goes to 0. And it's going to be this entire polynomial. And then it's minus the original. So what I'm going to do is I have to distribute the negative to all three of those terms. So that's minus 3x squared plus 2x minus 4. And now I want to see, does 3x squared minus 3x squared, negative 2x plus 2x, and 4 minus 4. So what we're left with is 6xh plus 3h squared minus 2h all over h. And now can an h factor out of my numerator? So we have h, and then we're left with 6x plus 3h minus 2. The h's divide. I can now plug in 0, and we're left with 6x minus 2. Is that what we needed to prove? It was. We got it. So the benefit of doing this, and now that we know that f prime of x is 6x minus 2, I can say to you, what's the derivative at 1? What's the derivative at 3? What's the derivative at 5? What's the derivative at negative 7? And all that would take is you taking these x values and plugging that in here to find the slope at every point, instead of finding the limit for each one of these x values. Oh, that's the same problem. Okay, so what does what does the derivative tell us graphically? If the derivative is positive, greater than 0, so this means that slope is positive, then the original graph is increasing. So if you think about a positive slope, that's when the original graph is going up. When the slope is negative, or the derivative is 0, or the derivative is, I'm sorry, less than 0, the derivative is negative, then the original graph is decreasing. Now when the slope is 0, or when the derivative equals 0, that's a critical value. And that's when the original graph has a maximum or minimum point. Like a parabola. If you think about a parabola, here the derivatives are positive, the slope, the graph is going up. At the max, the tangent line has a slope of 0, the derivative is 0, so it's a max or min. And then on this half, over here, all the tangent lines have negative slopes, meaning it's decreasing. Okay, so then for 3 last questions, here's a good quiz review question from what we did on Tuesday. Sketch the derivative for each of these functions. So we'll pause the video so you can practice that. Okay, so this first graph has a slope of 0 everywhere. So the derivative is a horizontal line of 0. This graph has a slope, if I count it, of 2 everywhere. So we have a horizontal line at 2. Okay, so then lastly, this third graph, remember a sharp point there, the derivative does not exist at 0. The derivative on the left piece, these are negative slopes of 1, and the right piece has a positive slope of 1. We have a negative slope of 1, but does not exist at 0. And on the right side, we had a positive slope of 1. So we have this jump discontinuity at 0. Okay, so your homework is page 19 in the packet. It's not all of the problems. Pay attention. It's 11, 13, 15, 17, 21, and 27. Try those. All of the answers will be on Edline. We could even pause the video here so you can check yourself.